Producing millions of bottles of Pepsi every single day requires an extreme level of precision and cutting-edge technology. Inside massive factories, high-speed machines mix the perfect blend of carbonation and sweetness before bottling and sealing at lightning speed. In this documentary, we take you inside the Pepsi production process, revealing the engineering behind one of the world's most popular soft drinks. The process of making Pepsi begins with one of its most essential components, water. Water forms the majority of the final beverage, making its purification and preparation one of the most critical steps in the manufacturing process. PepsiCo takes extreme care in sourcing and treating water to ensure the final product is free from impurities, contaminants, and off flavors. Without this careful preparation, the beverage could have inconsistencies in taste, appearance, and carbonation retention. The journey starts with sourcing water from natural springs, municipal supplies, or underground wells, depending on the bottling plant's location. However, regardless of its origin, this water must go through extensive treatment to meet PepsiCo's strict quality standards. The process begins with initial screening, where water passes through coarse filters that remove large particles such as dirt, sand, and debris. This is followed by sedimentation, a method that allows heavier impurities to settle at the bottom while the cleaner water moves forward in the process. Once the larger impurities are removed, the next step is carbon filtration. This step is crucial for removing chlorine, organic compounds, and any unwanted odors or tastes that could interfere with the Pepsi formula. Activated carbon filters contain a highly porous material that traps chemical impurities while allowing pure water to flow through. This process not only improves the taste of the water, but also enhances its ability to mix well with the other ingredients later in production. But up next is the reverse osmosis process, one of the most advanced purification techniques used in beverage manufacturing. Reverse osmosis involves forcing water through an ultra-fine membrane under high pressure, effectively removing even the tiniest dissolved particles, including salts, minerals, and microscopic contaminants. This ensures that the water is as pure as possible before it becomes part of the Pepsi formula. To further refine the water, it undergoes ultraviolet sterilization. This step is essential for eliminating any remaining bacteria, viruses, or other microorganisms that could compromise the safety and shelf life of the beverage. High-intensity UV light disrupts the DNA of these microorganisms, rendering them inactive without the use of chemical disinfectants. Finally, before the purified water is stored, it goes through an ozonation process. Ozone, a highly reactive form of oxygen, is injected into the water to act as a natural sanitizer. This step ensures that the water remains free from microbial contamination while it is held in large stainless steel storage tanks, awaiting the next phase of production. Now that the water has been meticulously purified, it must be precisely balanced to create the ideal base for Pepsi. Even though reverse osmosis removes most dissolved solids, a controlled amount of specific minerals is added back into the water to optimize taste and improve its ability to retain carbonation. This step is carefully monitored as the mineral composition of the water can impact the final mouthfeel and texture of the beverage. With the water fully prepared and stored in sanitary tanks, it is now ready to be mixed with the other key ingredients that will give Pepsi its distinctive flavor. But before moving on to mixing, each batch of purified water is rigorously tested for quality. Samples are taken from the storage tanks and analyzed in PepsiCo's in-house laboratories. Scientists and quality control experts measure pH levels, mineral content, and overall purity, ensuring that each batch meets the company's global standards. If any irregularities are detected, the water is either reprocessed or discarded, preventing any inconsistencies from affecting the final product. Now that the water has been meticulously purified and stored in sanitized tanks, the next crucial step in the Pepsi manufacturing process is the preparation and addition of sweeteners. Sweeteners play a fundamental role in defining the flavor profile of Pepsi, contributing to its signature taste while also affecting mouthfeel, viscosity, and overall balance. The selection, processing, and precise blending of these sweeteners are critical to ensuring that every bottle and can of Pepsi maintains consistency across different production facilities worldwide. In most regions, Pepsi is sweetened with high fructose corn syrup, a liquid sweetener derived from cornstarch. However, in some markets, particularly in countries where cane sugar is more widely available or preferred, sucrose from sugarcane or sugar beets is used instead. Regardless of the source, the sweetener must be carefully refined and processed before being added to the beverage. The journey of high fructose corn syrup begins with corn milling, where harvested corn is cleaned, steeped, and ground into a slurry to separate the starch from the fiber, protein, and germ. The extracted starch is then subjected to enzymatic processing, where it is converted into glucose. A second enzyme is introduced to transform a portion of the glucose into fructose, increasing its sweetness. The result is a thick, viscous syrup that is then further refined, filtered, and tested to ensure the correct balance of glucose and fructose. The most commonly used variety in soft drinks is HFCS 55, which contains approximately 55% fructose and 45% glucose, closely mimicking the sweetness profile of cane sugar. For regions that use sucrose instead of HFCS, the sugar is derived from either sugarcane or sugar beets. Sugarcane is harvested, crushed to extract juice, and then boiled to concentrate the sugar, forming crystallized sucrose. Sugar beets, on the other hand, are sliced and soaked in hot water to extract sugar, which is then purified and crystallized. In both cases, the raw sugar undergoes extensive refining to remove impurities and ensure a uniform, pure sweetener. Once the sweetener is ready, it must be dissolved into a concentrated syrup before being mixed with other ingredients. In a dedicated mixing tank, the high fructose corn syrup, or dissolved sucrose, is blended with purified water in precise proportions to create a uniform, sweetening solution. This syrup is continuously agitated to prevent crystallization and ensure a consistent texture. To maintain Pepsi's exact sweetness level, refractometers are used to measure the syrup's sugar concentration, ensuring it falls within the specified range. At this stage, the syrup is also subjected to rigorous quality control testing. Laboratory technicians take samples from each batch and analyze them for purity, consistency, and microbial safety. Any inconsistencies in sweetness or viscosity could alter the taste of the final product, so adjustments are made, if necessary, before moving on to the next step. Now that the sweetener has been perfectly prepared, it is time to introduce the key flavoring components that define Pepsi's distinctive taste. Pepsi's flavor is the result of a complex blend of natural and artificial flavorings, including citrus oils, spice extracts, and caramel notes. The exact recipe remains a closely guarded secret, known only to a select few within the company. But it is widely understood that ingredients like orange oil, lemon oil, vanilla, cinnamon, nutmeg, and cola nut extract contribute to the drink's signature profile. The flavoring components are carefully blended into a concentrated mixture known as the flavor base. This highly concentrated liquid is prepared in a separate, sterile mixing tank, where precise measurements of each ingredient are combined under controlled conditions. Some of these ingredients, particularly the essential oils, must be emulsified using stabilizers to ensure they mix properly with the water-based formula of Pepsi. Without proper emulsification, the oils could separate from the rest of the beverage, leading to inconsistent flavor distribution. Phosphoric acid is then added to the flavor base, providing Pepsi with its signature sharpness and tangy aftertaste. This acid also plays a crucial role in preserving the beverage by inhibiting microbial growth. The level of acidity is carefully controlled to balance the sweetness of the drink and enhance its overall flavor. Caramel color, which gives Pepsi its deep brown hue, is another essential ingredient added at this stage. This colorant is created by heating sugar compounds under controlled conditions, resulting in a stable and safe coloring agent. The intensity of the caramel color is strictly regulated to ensure that every bottle of Pepsi has the same visual appeal. Once the flavor base is complete, it must be thoroughly mixed with the sweetener solution to create the final syrup that will be used in the soft drink. This blending process takes place in large stainless steel tanks, where high-powered mixers ensure even distribution of all ingredients. The proportion of sweetener to flavor base is precisely measured, as even a slight deviation could alter the taste of the final product. Before the syrup is approved for use, samples are taken and analyzed in a quality control lab. Tests include pH measurement, viscosity checks, and sensory evaluations, where trained tasters confirm that the syrup matches Pepsi's standard flavor profile. These rigorous quality checks ensure that every batch of syrup is identical, maintaining Pepsi's global consistency. Once the syrup has passed all quality control tests, it is stored in temperature-controlled holding tanks, ready to be mixed with carbonated water. These tanks are kept under strict sanitary conditions to prevent contamination and preserve the integrity of the syrup. But up next is one of the most critical aspects of the Pepsi production process: carbonation. This step is responsible for the effervescence and refreshing sensation that consumers associate with soft drinks. Without proper carbonation, Pepsi would lose its signature fizz, altering the drinking experience. The process of infusing the beverage with carbon dioxide is both a science and an art, requiring precise control over temperature, pressure, and gas concentration. To begin the carbonation process, purified water is first chilled to near freezing temperatures. The reason for this is that carbon dioxide dissolves more efficiently in cold water than in warm water, ensuring maximum carbonation retention. The chilled water is then injected with high purity CO2 gas under controlled pressure, creating carbonated water. This water is then carefully blended with the pre-mixed syrup in an exact ratio, typically around 5 parts carbonated water to 1 part syrup. The precise proportion ensures the correct balance of flavor, sweetness, and fizziness in the final beverage. Maintaining the right level of carbonation is crucial, as it directly affects the mouthfeel and shelf life of the product. If the carbonation is too low, the drink will taste flat and less refreshing. If it is too high, the beverage may be overly acidic or cause excessive foaming during packaging. To ensure consistency, carbonation levels are continuously monitored using pressure sensors and dissolved CO2 analyzers. The newly carbonated Pepsi must now be handled carefully to prevent the loss of carbonation before packaging. At this stage, the beverage is kept under constant pressure in specialized holding tanks to maintain CO2 solubility. Any sudden release of pressure could cause the carbon dioxide to escape, resulting in a less fizzy drink. With the Pepsi now fully mixed, carbonated, and held under precise pressure conditions, the next step is bottling and packaging. This is one of the most intricate parts of the manufacturing process, requiring extreme precision, speed, and cleanliness to ensure that every bottle and can of Pepsi is filled, sealed, and prepared for distribution without losing carbonation or quality. The bottling process must take place in a sterile environment to prevent contamination, and the machinery involved operates at incredibly high speeds to keep up with global demand. The first part of this process involves the preparation of bottles and cans. Pepsi is available in a wide range of packaging formats, including glass bottles, aluminum cans, and plastic bottles made from polyethylene terephthalate. Each type of container has its own preparation requirements, but all must be thoroughly cleaned and sterilized before being filled. For plastic bottles, the process begins with small, preformed PET molds called preforms. These preforms are heated to a specific temperature and then rapidly inflated using high-pressure air inside a blow molding machine. This machine expands the preforms into their final bottle shape, ensuring uniform thickness and durability. The freshly molded bottles are then conveyed into a high-speed rinsing station, where they are thoroughly washed with filtered water and food-safe sanitizing agents to remove any potential contaminants. Glass bottles undergo a more rigorous cleaning process since they are often reused. They are first soaked in a high-temperature caustic solution to break down any residue from previous use, followed by multiple rinses with clean, filtered water. Finally, they pass through a steam sterilization chamber to ensure that no microorganisms remain. Aluminum cans, on the other hand, arrive at the bottling plant pre-formed and ready to be filled. However, before filling, they are sent through a high-pressure air jet cleaning system that blasts away dust and debris. Since aluminum cans are highly sensitive to corrosion, a thin food-safe lining is applied inside each can to prevent any reaction between the beverage and the metal. Now that the bottles and cans are fully prepared, the filling process can begin. The carbonated Pepsi is transported through a network of pressurized stainless steel pipes that maintain the beverage's optimal CO2 concentration and temperature. The filling machines operate at high speeds, capable of processing thousands of containers per minute. For PET and glass bottles, filling is done using gravity-based or counter-pressure filling systems. In a counter-pressure system, the bottle is first pressurized with CO2 before the Pepsi is introduced. This prevents foaming and excessive carbonation loss during filling. The precise amount of liquid is dispensed into each bottle, with sensors ensuring that no underfilled or overfilled bottles proceed down the production line. Aluminum cans require a slightly different approach. Since they are more prone to CO2 loss due to their wide openings, the filling nozzles are designed to minimize turbulence as the liquid enters. The cans are quickly filled and then topped with a small injection of nitrogen gas to prevent oxidation before being sealed. Now that the containers are filled with carbonated Pepsi, the next critical step is sealing. This process must be done immediately after filling to prevent carbonation loss and contamination. For plastic and glass bottles, this involves capping. Screw-on plastic caps are applied to PET bottles using high-speed rotary capping machines, which tighten each cap with precise torque to ensure a secure seal. Glass bottles, often used for premium or international markets, are sealed with either metal crown caps or twist-off caps, depending on the region. Aluminum cans are sealed using a double seaming process. A lid, which contains an integrated pull tab, is placed on top of the can and then mechanically crimped around the rim. This creates an airtight seal that locks in carbonation and prevents leakage. With all the containers now sealed, they move on to the quality control phase. At this stage, random samples are pulled from the production line and tested for multiple factors, including fill level, carbonation retention, pressure stability, and contamination. Advanced X-ray and laser scanning systems inspect each bottle and can to ensure that there are no foreign particles, dents, or defects in the packaging. Any defective units are immediately rejected and removed from the batch. Once the beverages pass quality control, the containers proceed to labeling. Each bottle and can receives a label that includes branding, nutritional information, ingredient lists, and regulatory compliance markings. PET bottles have labels applied using heat shrink or pressure-sensitive label machines, while aluminum cans typically have their designs pre-printed onto the metal surface. After labeling, the bottles and cans are grouped into multi-packs for retail distribution. This process involves bundling them into various configurations, such as 6-packs, 12-packs, or full cases. Plastic shrink wrap, cardboard trays, or molded carrying handles are used to secure the multi-packs for easy transportation. The completed packs are then stacked onto pallets in an organized manner and wrapped in stretch film to stabilize them for shipping. Now it's time for one of the most logistically challenging aspects of Pepsi production: distribution. The pallets of finished Pepsi products are moved to temperature-controlled warehouses where they are stored before being shipped to retailers, grocery stores, vending machines, and restaurants. Since Pepsi is produced in enormous quantities to meet global demand, distribution logistics must be precisely managed to ensure that every store and vendor receives fresh products. Pepsi's supply chain is a highly coordinated operation involving fleet management, refrigerated storage, and just-in-time delivery systems. Large distribution centers act as hubs where shipments are sorted based on region and customer demand. Trucks, rail transport, and even cargo ships are used to move massive volumes of Pepsi across countries and continents. Once the products arrive at their final destinations, they are placed in cold storage or directly onto store shelves. In grocery stores and supermarkets, Pepsi is often stored in temperature-controlled sections to maintain freshness. Restaurants and fast food chains receive large volumes of Pepsi in bulk containers, which are connected to soda fountains for on-demand dispensing. Throughout this entire process, PepsiCo maintains strict inventory tracking and quality assurance programs. Each batch of Pepsi is assigned a unique tracking code, allowing the company to trace products back to their production date, location, and ingredient sources. This ensures that in the event of a recall or quality issue, affected products can be quickly identified and removed from circulation. With the Pepsi bottles and cans now filled, sealed, labeled, and packed for distribution, one of the final but most crucial aspects of the manufacturing process is ensuring product consistency, longevity, and consumer satisfaction. Maintaining Pepsi's signature taste and quality across millions of bottles and cans requires an advanced system of quality control, storage optimization, and packaging innovation. Every aspect, from the shelf life of the product to the materials used in packaging, plays a role in ensuring that each Pepsi delivered to a consumer is as fresh and enjoyable as the last. The first key factor in Pepsi's shelf life and consistency is its ability to retain carbonation over time. Carbonation, which gives Pepsi its signature fizziness, is created by dissolving carbon dioxide into the liquid under high pressure. The challenge is ensuring that this CO2 remains trapped within the beverage from the moment it is bottled until it is opened by the consumer. To maintain carbonation, Pepsi uses specially designed bottles and cans that act as airtight barriers, preventing CO2 from escaping. Plastic bottles made from polyethylene terephthalate are engineered with multiple layers that slow down gas diffusion, preventing CO2 from seeping out over time. The thickness and structure of PET bottles are carefully optimized to balance durability with weight, ensuring that the bottles are strong enough to retain carbonation while remaining lightweight for transportation. Aluminum cans provide an even better barrier against gas loss. Their completely sealed structure ensures that no CO2 escapes, preserving the drink's fizziness for extended periods. Additionally, a protective food-grade lining inside each can prevent any reaction between the metal and the beverage, which could otherwise affect flavor. Glass bottles, often used for premium markets or limited edition versions of Pepsi, offer the best gas retention of all packaging types. Glass is completely impermeable, meaning that Pepsi stored in glass bottles maintains its carbonation for the longest period. However, glass is heavier and more fragile than plastic or aluminum, making it less practical for mass production and distribution. Another critical factor in product longevity is preventing oxidation. Exposure to oxygen can alter the taste of Pepsi, causing it to become flat and develop off flavors over time. To counter this, PepsiCo employs nitrogen dosing in certain packaging lines. This process involves injecting a small amount of nitrogen gas into PET bottles just before sealing. The nitrogen displaces any residual oxygen inside the bottle, reducing the risk of oxidation while also adding structural rigidity to the bottle, preventing it from collapsing under vacuum pressure. Beyond carbonation and oxidation control, preservatives also play a role in maintaining Pepsi's freshness. While the beverage's acidity and carbonation naturally inhibit microbial growth, additional preservatives such as sodium benzoate are included to extend shelf life further. These preservatives prevent mold, yeast, and bacterial growth, ensuring that Pepsi remains safe for consumption for months or even years after production. Now that the beverage's stability is secured, it must be stored and transported under optimal conditions. Pepsi is highly sensitive to temperature fluctuations, which can affect carbonation retention and overall flavor. As a result, warehouses, distribution centers, and retail storage areas are kept within a controlled temperature range to prevent heat exposure. Excessive heat can accelerate CO2 loss in plastic bottles and increase oxidation reactions, leading to a flatter, less refreshing drink. To counteract this, refrigerated warehouses are used in regions where high temperatures could compromise product quality. During transportation, trucks equipped with climate control ensure that Pepsi is not exposed to extreme heat or direct sunlight, both of which could degrade the beverage. Another major factor that affects Pepsi's taste consistency is the impact of light exposure. Ultraviolet light can break down some of the organic compounds in Pepsi's flavoring, leading to unwanted taste changes. This is why Pepsi bottles, particularly those made from PET, are designed with tinted or opaque plastic to reduce UV penetration. Aluminum cans and glass bottles naturally provide complete light protection, further ensuring product stability. Once Pepsi reaches its final retail destinations, whether in grocery stores, vending machines, or fast food chains, it is crucial that storage guidelines continue to be followed. Retailers are instructed to keep Pepsi stock rotated, ensuring that older products are sold first and newer shipments are stored properly. This helps maintain product freshness for consumers while preventing expired stock from sitting on shelves. Fast food chains and restaurants that serve Pepsi from soda fountains have additional steps to ensure taste consistency. Instead of pre-packaged bottles and cans, Pepsi is delivered to these locations in large pressurized syrup containers known as bag-in-box systems. These containers hold concentrated Pepsi syrup, which is mixed with carbonated water on demand through specialized dispensing machines. The bag-in-box system allows for efficient storage and prevents waste, as restaurants can control the syrup-to-water ratio for optimal taste. These systems are regularly maintained, with filters and carbonation settings adjusted to match the ideal flavor profile. Additionally, PepsiCo provides restaurants with quality control tools to measure CO2 levels and syrup concentration, ensuring that every poured glass tastes as good as a bottled Pepsi. With all these measures in place, Pepsi is now fully ready for consumers to enjoy. But beyond the immediate production and distribution, PepsiCo continually invests in research and development to improve manufacturing efficiency, sustainability, and packaging innovations. One of the company's most significant focuses in recent years has been reducing the environmental impact of its packaging. PepsiCo has made major advancements in recyclable PET bottle technology, developing bottles that contain post-consumer recycled plastic to cut down on waste. Additionally, the company has experimented with plant-based PET alternatives that reduce reliance on petroleum-based plastics. Aluminum cans have also been a major target for sustainability improvements. Since aluminum is highly recyclable, PepsiCo has worked to increase the amount of recycled aluminum used in can production. The company encourages consumers to participate in recycling programs, ensuring that cans are properly collected and reused. In some markets, PepsiCo has even introduced refillable glass bottle programs, allowing consumers to return used bottles for sanitation and reuse, significantly cutting down on single-use waste. Further technological advancements in bottling machinery have also improved efficiency in the production process. While the Coca-Cola Company maintains control over the flavor concentrate, the bottling partners are responsible for the bulk of production, mixing, bottling, packaging, and distribution. But before anything is mixed, the most vital ingredient must be treated first: water. Water makes up over 85% of Coca-Cola, and its quality directly affects the flavor, clarity, and shelf life of the product. Municipal water is drawn into the plant and subjected to an advanced, multi-stage purification process. It begins with coarse filtration to remove sediment and particulates. From there, the water passes through activated carbon beds, where chlorine and organic compounds are stripped out. Next comes reverse osmosis, or ultrafiltration membranes, which remove dissolved salts, metals, and microorganisms. This purified water then undergoes ultraviolet light treatment, or ozonation, to ensure biological sterility. The goal is to achieve ultra-pure, neutral-tasting water that provides a blank canvas for the Coca-Cola flavor. Constant inline sensors monitor for pH, turbidity, and conductivity, ensuring every liter meets exacting standards before it ever touches the syrup. Next, the flavor base is prepared. The concentrated Coca-Cola syrup arrives at the factory in sealed, food-grade containers. Its precise formulation remains a closely guarded secret, known internally as Merchandise 7X. What we do know is that the concentrate contains sweeteners, acids, caramel coloring, caffeine, natural flavors, and essential oils derived from citrus peels and spices. This concentrate is mixed on-site with additional ingredients, often in a syrup blending station, to create a finished syrup. The syrup blending process is conducted in stainless steel tanks equipped with high-shear mixers and recirculation pumps. These ensure the thick concentrate is uniformly mixed with water, sweeteners, and phosphoric acid, one of the key flavor-defining agents. In most regions, high fructose corn syrup is used as the sweetener, though in others, such as Mexico and parts of Europe, cane sugar is used instead. The blending tanks are temperature controlled and sealed to avoid contamination, and every batch is sampled and lab tested before moving forward. With the syrup mixed and the water purified, the next step is combining the two. This happens in a piece of equipment known as a proportioner. Here, the syrup and treated water are blended at precise ratios, usually around 1 part syrup to 5 parts water, under tight quality control. The proportioner ensures the mix is homogeneous and delivers the same flavor intensity in every can or bottle, no matter where it's made in the world. Now comes the science of carbonation. Carbon dioxide gas, stored in large pressurized tanks on site, is injected into the finished beverage mixture using a carbonator. The carbonator chills the liquid to just above freezing, typically around 33 to 38 degrees F, because cold water can hold more dissolved gas. The beverage passes through a sintered stainless steel sparger, or fine bubble diffuser, which allows the CO2 to saturate the liquid evenly. This gives Coca-Cola its signature effervescence, a process carefully controlled to maintain consistent volumes of CO2, typically between 2.5 and 3.0 volumes. At this stage, the finished product, cold, carbonated Coca-Cola, is transferred to an insulated holding tank under gentle pressure. From here, it is ready to be packaged. And this is where the production line truly comes to life. In a modern bottling plant, packaging lines run at astonishing speeds, filling and capping up to 1,200 bottles per minute or more. But before any beverage enters a container, the containers themselves, whether glass bottles, plastic PET bottles, or aluminum cans, must be cleaned and prepared. PET bottles arrive pre-formed and are blown into full-size bottles on site using a stretch blow molding machine. This reduces transport volume and increases efficiency. Once formed, each bottle is rinsed or sterilized using ozonated water or clean steam. This eliminates microbial contamination and dust particles. Cans and glass bottles undergo similar sterilization processes, often involving high-pressure air jets or a tunnel washer that uses multiple rinsing stages. Clean containers then move into the filling carousel. This is a high-precision rotary filling machine with dozens of synchronized nozzles, each calibrated to deliver exactly the right volume of Coca-Cola into each bottle or can. The filling occurs under pressure to prevent foaming and loss of carbonation. A vacuum seal may be briefly applied to ensure the gas stays dissolved in the liquid. Immediately after filling, the containers move along the carousel to the capping or sealing station. For PET bottles, tamper-evident screw caps are applied using torque-controlled capping heads. For cans, an aluminum lid is crimped on using a seamer. Glass bottles receive a crown cap applied with pneumatic presses. These closures are crucial not only for sealing in freshness, but also for maintaining carbonation levels throughout the product's shelf life. Once sealed, containers move rapidly to the date coding and inspection stations. Here, inkjet printers mark each unit with its production time, lot number, and best before date. Simultaneously, high-speed cameras and check weighers verify fill levels, cap integrity, label alignment, and overall container quality. Any anomaly triggers a pneumatic arm to remove the item from the line instantly. Bottles and cans are then grouped and packed for shipping. Smaller units may be shrink-wrapped into 6-packs or inserted into cardboard carriers. Larger cases are assembled by robotic arms into corrugated boxes or pallet layers. Palletizers stack the boxes into tall, stable configurations and apply barcoded stretch wrap for secure transport. At this point, Coca-Cola is nearly ready to leave the facility, but not before one last layer of control. Samples from every batch are retained and sent to the quality assurance lab, where a battery of tests is performed. These include sensory evaluations by trained tasters, gas volume testing with CO2 analyzers, Brix level measurement to confirm sweetness, and acid titration for pH control. Only after passing all these checkpoints is the batch released for distribution. The finished product is stored in a climate-controlled warehouse, maintained at ideal conditions to prevent spoilage or bottle expansion. From here, the Coca-Cola is dispatched via refrigerated trucks or temperature-monitored dry vans. Logistics teams coordinate shipments to supermarkets, restaurants, vending distributors, and retail centers using inventory tracking systems that ensure first-in, first-out rotation and traceability in case of recalls. Behind the scenes, the entire system is monitored by a sophisticated SCADA platform that links water purification, blending, carbonation, and packaging into a unified, real-time control interface. Operators can adjust flow rates, tank temperatures, carbonation pressure, and even cap torque from centralized dashboards. Predictive maintenance alerts notify technicians when pumps, motors, or valves deviate from baseline performance, minimizing downtime. The scale is immense. A single Coca-Cola bottling facility can produce several million units per day across various formats, ranging from 8 Oz cans to 2-liter bottles, each undergoing its own production and packaging parameters. Automation is essential, but so is human oversight. Technicians, engineers, microbiologists, and logistics experts all play vital roles in ensuring every sip of Coca-Cola tastes exactly as it should, whether it's opened in Atlanta, Tokyo, or Cape Town. And yet, for all its complexity, the experience of drinking Coca-Cola remains simple: effervescent, sweet, slightly acidic, and unmistakably iconic. Each bottle is a product not just of secret formulas and clever marketing, but of some of the most advanced food manufacturing systems on Earth. From water chemistry to high-speed robotics, From syrup tanks to palletized crates, Coca-Cola's journey from factory to fridge is a meticulously choreographed process, engineered for both speed and perfection. To begin understanding how Dr. Pepper is made, we have to step inside one of the massive regional bottling facilities operated by licensed partners. These plants are the heartbeat of the Dr. Pepper supply chain. They don't just bottle soda, they engineer precision, maintain sterility, and manage staggering volumes of ingredients with scientific exactness. Everything begins with water. Although soda is often celebrated for its flavor, more than 85% of the final product is purified water. And not just any water, ultra-clean, neutral, flavorless water that forms the foundation of every bottle. This means municipal or groundwater entering the plant must undergo intensive treatment. The first stage of this treatment process uses coarse filtration to remove large particles and suspended solids. Then, the water is passed through activated carbon beds to eliminate chlorine, chloramines, and any volatile organic compounds that could distort the flavor. From there, the process shifts to more advanced techniques. Reverse osmosis membranes, or ultrafiltration units, strip the water of minerals, microbes, and trace contaminants. Ultraviolet light, or ozonation, finishes the process, sterilizing the water and rendering it free of any taste or odor. The water is now ready, perfectly clean, chemically stable, and ready to receive the flavors that define Dr. Pepper. Parallel to this, syrup preparation takes place in a separate, sanitized mixing room. The base flavoring for Dr. Pepper arrives at the plant in concentrated form, pre-blended by the brand's flavor division under tight secrecy. These concentrates are stored in stainless steel containers and handled with care, with operators measuring and metering the required amounts into large batching tanks. In these tanks, often fitted with high shear mixers, agitation paddles, and precision load cells, the base concentrate is combined with purified water, sweeteners, and acids. Depending on the region, the sweetener may be high fructose corn syrup or cane sugar. The acid, usually phosphoric or citric, helps balance the syrup's pH and sharpness. The mixture is stirred and recirculated until it becomes a uniform, homogeneous syrup with exact Brix values, the measure of dissolved solids in a liquid, often used to calibrate sweetness levels. Before it moves forward, the syrup batch undergoes quality assurance checks. Technicians take samples and run tests in on-site labs, analyzing Brix, pH, color, and aroma. Only after it passes these strict controls is the syrup cleared for the next phase, beverage blending. In a process called proportioning, the syrup is metered and blended with purified water in exact ratios, typically around 1 part syrup to 5 parts water. This mixture becomes the flat, uncarbonated Dr. Pepper base. The proportioning system is controlled by flow meters and programmable logic controllers, ensuring that the mix is stable within a tight tolerance band. Every shift, every batch, whether it's in Texas, Ontario, or the Philippines, must deliver the same flavor profile. With the beverage mixed, it's time to add the fizz. Carbonation is one of the most technically critical steps in soda production. The pre-mixed Dr. Pepper is chilled to just above freezing, typically around 35 degrees, to increase its ability to absorb carbon dioxide. CO2 is stored in large tanks on site and is food grade, filtered, and monitored for purity. The cold liquid is forced through a carbonator where fine CO2 bubbles are injected under high pressure through porous diffusers or sintered steel plates. Proper carbonation is both science and art. If done poorly, the soda may foam excessively during bottling or taste flat when opened. The target for Dr. Pepper is usually around 2.5 to 3.0 volumes of CO2, enough to give it its characteristic zing without overwhelming the complexity of its 23 flavor blend. The carbonated product is now pressurized and ready for immediate bottling to prevent CO2 loss. The bottling line is where everything shifts into high speed. Depending on the plant, the line can handle glass bottles, aluminum cans, or PET plastic bottles. Most modern facilities use stretch blow molding machines to convert PET preforms into full-sized bottles on site. This reduces shipping costs and allows for rapid size changes depending on demand. Each bottle or can first passes through a rinsing or sterilizing system. Bottles may be inverted and blasted with ionized air or washed with ozonated water. Cans are typically rinsed with sterilized water before entering the filler. Now, the carbonated Dr. Pepper is dispensed into containers using a rotary filling machine. This machine features multiple filling heads rotating on a carousel, with each head delivering the precise amount of liquid into each container. The filler operates under pressure to prevent foam and retain carbonation. As soon as the beverage is deposited, the bottle or can is sealed. PET bottles are capped using torque-controlled screw heads, while cans receive crimped-on aluminum lids in a high-speed seamer. Immediately after sealing, the containers pass under printers that apply batch codes, production dates, and expiration information. This coding is essential for traceability. If there's ever a recall or quality issue, the plant can trace every bottle back to the exact minute it was produced, the syrup batch used, and the operator on duty. Then comes packaging. Filled bottles are grouped into packs using shrink film, cardboard sleeves, or trays, depending on the final retail format. These packs are stacked by robotic arms onto pallets in precise configurations optimized for transport. The finished pallets are stretch wrapped, labeled with shipment data, and moved to the distribution warehouse. But before any pallet is cleared for shipment, the line's quality control team pulls samples from each production run. These are subjected to rigorous testing in the plant's on-site laboratory. Pressure tests confirm carbonation levels. Spectrophotometers check color uniformity. Sensory experts conduct taste evaluations to verify the blend is balanced. Microbial samples are incubated to ensure the product is sterile and safe. Meanwhile, automation software monitors the entire plant. From SCADA systems that track syrup bricks and carbonation pressures to IoT-enabled sensors that measure temperature drift in holding tanks, the entire operation is visible in real time to engineers and technicians. If a motor starts to overheat or a fill level goes out of spec, alerts are triggered immediately. Once quality is assured, the finished product is ready for shipping. Climate-controlled logistics routes transport Dr. Pepper to warehouses, distributors, and retail outlets. Some trucks are refrigerated, especially in hotter regions, to protect the product during transit. Whether it's a vending machine in a high school, a 12-pack in a grocery store, or a fountain soda in a fast food chain, each container of Dr. Pepper must taste exactly the same. And that's only possible because every variable was controlled from start to finish. Beyond the factory, the Dr. Pepper production network also includes specialty manufacturing for fountain syrups, bag-in-box formats for restaurants, and concentrate shipments for international bottlers. These formats go through similar blending, filtration, and quality assurance processes, but are tailored for bulk use with different bricks and carbonation considerations. Every day, this system repeats across dozens of plants, with millions of cans and bottles produced and shipped with extraordinary consistency. Despite being made at different locations by different teams, every unit of Dr. Pepper shares the same flavor fingerprint: sweet, spicy, slightly fruity, with a creamy undertone and a signature bite. It's a beverage born in the 1880s, but produced today using some of the most advanced technologies in food manufacturing. From its mysterious blend of flavors to its perfectly balanced carbonation, Dr. Pepper represents a legacy of innovation, precision, and a dedication to quality that extends from syrup tank to store shelf. Sprite's story begins with water. While most people focus on Sprite's citrus flavor, the truth is that over 85% of what you're drinking is water. But not just any water. For Sprite to taste exactly the same in Singapore as it does in San Diego, bottling plants must purify their local water supply to a consistently neutral baseline, free from taste, color, odor, and minerals. The incoming municipal or well water is first screened through mechanical filters to remove suspended solids. It then moves through activated carbon filters that strip out chlorine, chloramines, and any volatile organic compounds. This ensures that the water has no off-putting flavors. Then it passes through either reverse osmosis membranes or demineralization columns, which remove dissolved salts and ions. Finally, a UV treatment or ozone injection kills any microorganisms. This ultra-purified water is held in stainless steel tanks, where it is monitored in real time for pH, conductivity, turbidity, and microbial counts. It must meet the exact specifications set by the Coca-Cola company before being allowed into any part of Sprite production. Only once it's passed all quality checkpoints can it be used to create the base for one of the world's most recognizable sodas. Parallel to the water treatment is the preparation of Sprite's proprietary flavor syrup. This part of the process is handled in a syrup blending room, often kept under positive air pressure and high sanitation standards to prevent contamination. The base concentrate used for Sprite, supplied by the Coca-Cola company, is delivered to the plant in sealed, food-safe drums or totes. This concentrate contains the citrus flavoring system, acidulants, and trace aromatic compounds that define Sprite's lemon-lime taste. Inside the blending tanks, equipped with high-torque agitators and recirculation loops, the concentrate is mixed with water and sweeteners to form the final syrup. The sweetener is usually high fructose corn syrup in the United States, though in some countries, cane sugar is used instead. Citric acid and natural flavors help create that sharp, clean taste. The syrup is blended at specific Brix levels, a measure of sugar concentration, and is analyzed for consistency in labs adjacent to the blending floor. Once the Sprite syrup is blended and passes quality checks for color, taste, pH, and sugar content, it is sent to the proportioning system. This is where the final product begins to take shape. Inside stainless steel pipelines, the syrup is carefully metered and mixed with the purified water in precise ratios, generally around 1 part syrup to 5 parts water. This mixture is now the uncarbonated version of Sprite, flat, sweet, and citrusy, but still missing that all-important sparkle. Carbonation is added in the next step. The flat beverage mixture is chilled to near freezing, typically 33 to 36 degrees F, inside jacketed holding tanks. This is essential because cold water absorbs carbon dioxide much more effectively. A carbonator, one of the most critical pieces of equipment in the line, injects high-purity, food-grade CO2 into the chilled mix. The carbonation process is highly controlled. Bubble size, saturation level, and gas purity are all continuously monitored. Sprite generally carries between 2.7 to 3.0 volumes of CO2, giving it that signature effervescence and a sharp bite that enhances the citrus flavor. Once carbonated, the finished Sprite beverage is held under pressure in chilled, oxygen-free holding tanks. It is now ready for bottling, and this is where the production line hits its highest speed. The bottling line is a marvel of automation, capable of processing over 1,000 bottles or cans per minute, all synchronized to fill, cap, label, and inspect each unit with zero tolerance for error. First, the containers must be prepared. If PET bottles are used, they arrive as pre-forms, small, test tube-shaped blanks. These pre-forms are heated and stretch-blown into full-size bottles using high-pressure air inside precision molds. This process allows plants to manufacture bottles on-site, reducing shipping costs and allowing for quick changes in size or shape depending on market needs. The newly formed or delivered containers are then sent through a rinsing or sterilizing station. Bottles may be sprayed with ionized air, steam, or ozonated water to remove dust and kill microbes. Cans are similarly rinsed and then inverted before filling. The carbonated Sprite is then filled into each container using a rotary filling machine. The beverage must be filled under counter pressure to preserve carbonation and prevent foaming. Each filling nozzle is calibrated to deliver an exact volume, down to fractions of a milliliter. As soon as a bottle is filled, it immediately passes to the capping station. Caps and lids are fed in from hoppers and applied with high-speed capping heads that torque each Piet bottle to specification. Aluminum cans are sealed with a crimping mechanism called a seamer, which attaches the lid using multiple rollers in rapid succession. The entire filling and capping sequence is enclosed within a clean, sterile zone to prevent contamination. With the product sealed, it's time for coding and inspection. Each unit is printed with a production code, batch number, and best before date using a high-speed inkjet or laser printer. Advanced camera systems immediately scan the bottles or cans for fill level, cap alignment, label position, and structural defects. Anything that doesn't meet specs is ejected from the line automatically. Now the finished bottles or cans are routed to the packaging area. Depending on the destination, they may be shrink-wrapped in multi-packs, inserted into cardboard carriers, or loaded into trays for larger retail formats. Robotic palletizers pick up these packs and stack them in precise layers, forming stable shipping units. Each pallet is stretch-wrapped, labeled with destination and production information, and scanned into the warehouse inventory system. Before these pallets leave the facility, the Sprite they contain has already been sampled for in-depth quality checks. Laboratory technicians pull random samples throughout each production run and test for bricks, pH, CO2 volumes, and sensory characteristics such as aroma, clarity, and taste consistency. These tests are performed hourly, sometimes more frequently, using calibrated instruments and trained panels. Additional microbiological testing ensures the beverage is free of spoilage organisms. Each batch must pass these hurdles before it is released for distribution. Some plants hold back every 10th or 20th pallet for additional hold and release protocols, where the beverage is stored under controlled conditions and monitored for early spoilage signs before shipment. From here, Sprite enters the logistics phase. Temperature-sensitive loading docks ensure that the product stays cool, especially in hot climates where carbonated beverages can suffer from premature expansion or loss of pressure. Climate-controlled trucks or standard dry vans, depending on the geography, transport the soda to distribution centers, retail warehouses, and vending machine operators. Behind the scenes, the entire operation is driven by powerful software, SCADA systems, programmable logic controllers, and cloud-connected ERP platforms. These monitor tank levels, syrup usage, CO2 flow rates, batch records, and even maintenance needs. Some lines are equipped with predictive analytics, using data to forecast failures before they occur, reducing downtime and ensuring maximum uptime. Every bottle and can of Sprite must conform to the same flavor fingerprint: balanced sweetness, bright citrus notes, clean finish, and a bracing level of fizz. Even with local water, different sweeteners, and various bottling partners worldwide, Coca-Cola's stringent standardization process ensures that no matter where you are, every Sprite you open tastes like it came from the same source. And yet, as science-driven as it is, the drink remains simple in experience. No caffeine, no color, just a bold, clear, citrus-flavored soda that delivers a refreshing hit with every gulp. A product of incredible precision, born in stainless steel tanks, shaped by sensors, robotics, and human craftsmanship, and enjoyed, often without a second thought, by millions. In the end, Sprite may be light and fizzy, but its production is anything but. It's the result of decades of process optimization global logistics, sensory chemistry, and industrial control. And behind that cool green label lies one of the most tightly controlled and fascinating beverage production systems in the world. Pepsi begins with water, ordinary in origin, but transformed through an intense purification system. First, the water flows through mechanical filters, stripping out any visible particles. It moves next into activated carbon beds, where chlorine, organic residues, and odors are removed. Then it's pushed through reverse osmosis membranes under high pressure, leaving behind salts, microbes, and trace contaminants. A final sweep of ultraviolet light and ozone leaves the water sterile, mineral-free, and chemically neutral. This is the blank canvas. The next stage injects character. Deep inside jacketed mixing tanks, a thick amber concentrate is created. Liquid sugar surges through stainless steel lines into the tank, met by metered doses of colorants, acids, caffeine solution, and the core flavor compound. Inside the vessel, high-speed impellers shear the mixture into uniformity. The liquid darkens, thickens, and becomes the syrup that defines the drink's signature base. Flow meters and refractometers verify sugar density to the decimal. Agitators spin in controlled bursts. A small shift in temperature or pH would trigger instant correction by the automated control system. Once blended, the syrup doesn't wait. It flows straight into a proportioning unit, where it meets the ultra-purified water. Two pressurized lines merge into one, and precisely tuned valves blend them in a 5-to-1 ratio. The new mixture forms a complete beverage. Almost. First, it's sprayed into a vacuum chamber. This fine mist encounters low pressure and a cloud of CO2. Oxygen is stripped away. The liquid is chilled rapidly to near freezing, lowering its ability to resist carbonation. Inside the carbonation vessel, thousands of microscopic pores inject CO2 with exact pressure. The liquid churns gently in a sealed chamber, held under 4 bar of pressure at 0 to 2 degrees Celsius. Gas dissolves silently. Bubble size, saturation rate, and temperature are monitored in real time. When carbonation reaches target levels, the drink exits the vessel with all of its effervescence locked in. On another line, PET bottle preforms arrive in rapid succession. Each one is gripped by a rotary arm and passed through infrared heaters. The plastic softens and glows dull red before entering the blow mold cavity. High-pressure air inflates it in a fraction of a second, pressing it against the steel mold's walls to form a full-size bottle, contoured, clear, and warm to the touch. It exits the mold and cools on contact with the conveyor air. Bottles enter the rinsing carousel, where they're inverted and blasted internally with sterilized water. As they flip upright again, air knives dry the insides instantly. Next, they move toward the isobaric filler, a rotary machine that maintains pressure equilibrium between the drink and the container. Each bottle is clamped beneath a filling valve. CO2 gas is injected first to pressurize the empty space. Then the valve opens, and the drink enters from the base, rising smoothly with minimal turbulence. Foam is avoided. Gas is preserved. The moment filling is complete, the bottles roll to the capper. Here, precision torque heads spin blue caps onto each neck. A magnetic clutch delivers exact closing force, tight enough to seal, loose enough to open later. Inline torque sensors confirm every closure. Any outliers are ejected instantly by a compressed air nozzle. From there, each sealed bottle passes under a jet printer that marks it with time, date, and batch code. The ink dries in under a second. A vision system verifies code presence and clarity. Another camera checks fill level and cap alignment. Each bottle is under constant scrutiny as it moves down the line at hundreds per minute. Labels come next. A roll-fed applicator unwinds pre-printed film and cuts each label to size. As bottles spin past, a roller applies adhesive, wraps the label, and smooths it with a brush. The result is a seamless, wrinkle-free appearance with perfect alignment. Sensors detect any offset and make micro-adjustments on the fly. Now grouped into formation, the bottles move toward bundling. A collator arranges them into packs, 6, 12, or 24, depending on the format. Shrink film is draped over each group and heat sealed at the seams. The entire bundle then passes through a shrink tunnel where hot air circulates in tight zones. The film tightens instantly, locking the bottles together in a rigid block. Bundled packs exit the tunnel and head for palletizing. Robotic arms swing overhead, guided by vision cameras and programmed stacking patterns. Grippers lift multiple bundles at once and layer them on wooden pallets. Slip sheets are inserted between tiers by a vacuum-fed arm. Once stacked, the entire pallet is conveyed into a stretch wrapper. A rotating arm winds clear film around the stack in tight spirals, binding the load into one secure shipping unit. Meanwhile, cans run on a parallel line. Massive depalletizers feed columns of aluminum cans into a rinsing tower. From there, the empty cans travel into another isobaric filler designed specifically for pressurized metal packaging. Liquid fills the cans from the bottom. A seamer spins down a lid, hooks the metal under the rim, and crimps it tight. A double seam forms, locking the gas inside with extreme precision. Cans are inverted, jet-coated, vision inspected, and shrink-wrapped in trays. Robotic stackers build them into pallet loads at similar speed to the bottle line. Both packaging lines converge in the same warehouse zone, where outbound conveyors feed the finished pallets toward refrigerated staging docks. Each section of the line is governed by PLCs. These controllers monitor temperature, fill height, carbonation levels, syrup ratios, and packaging counts. Real-time data appears on SCADA terminals, allowing operators to adjust line speed, diagnose faults, and fine-tune performance without stopping production. If any parameter drifts out of tolerance, such as syrup bricks, carbonation pressure, or label alignment, the system either autocorrects or halts the affected module. Clean-in-place systems activate between product runs. Valves switch flow from production mode to cleaning mode. Heated alkaline solution flushes through all contact surfaces, syrup tanks, filler bowls, carbonators, valves, and pipes. Sensors track flow rate and chemical concentration. After the caustic wash, a water rinse clears residue, followed by a sanitizing flush. No disassembly is required. The entire cleaning cycle is automated and logged. During operation, bottle speeds exceed 60,000 units per hour. Carbonation tanks maintain saturation levels within plus 0.05 volumes. Fill levels are accurate to within plus and 1.5 milliliters. Every step, from syrup blending to cap torque, is governed by tolerances and feedback loops. When the process runs at full speed, hundreds of meters of conveyor synchronize bottle spacing, curve speed, and back pressure control. Star wheels, diverters, and sensors ensure smooth flow with no collisions. Air conveyors keep lightweight empty bottles suspended and aligned without touching mechanical guides. Pepsi's production system is built for non-stop performance. Each component, carbonator, blow molder, labeler, filler, capper, bundler, is modular and servo-driven. Changeovers for different bottle sizes or formats require only a software switch, a tooling exchange, and a calibration cycle. The entire system adapts to new production schedules without downtime. Fanta production starts with water, but it cannot be ordinary. The raw supply flows into a filtration system where coarse particles are stripped away. From there, the water passes through activated carbon beds to remove chlorine and organic traces. Next, it enters a reverse osmosis membrane under pressure, separating out salts, metals, and microbes. At this stage, the water is nearly sterile. A final ultraviolet treatment and ozone injection complete the purification. Now the water is neutral, flavorless, and ready for transformation. Inside a stainless steel mixing tank, the drink's base is constructed. A stream of refined liquid sugar is pumped in through insulated lines. Dosing pumps feed in controlled quantities of citric acid, natural fruit flavors, stabilizers, preservatives, and vibrant colorants. The tank's agitators rotate at set intervals to blend the ingredients evenly. Every element is added with exactitude. Flow meters regulate sugar volume. Acid concentration is tracked by inline pH sensors. Color intensity is verified with optical density readers. The mixture is continuously monitored for consistency. Temperature is held between 15 and 20 degrees Celsius. If any reading deviates from target, the control system halts the process and recalibrates dosing in real time. Once the syrup reaches specification, it is transferred to a buffer tank where it rests briefly under agitation, held at a constant temperature and protected from ambient air. Next, the beverage is formed through a high-speed proportioning system. The syrup is combined with the purified water in a fixed ratio, generally around 1 part syrup to 5 parts water. This is managed by synchronized flow meters and control valves. The blending occurs in line, with turbulence in a stainless steel chamber, ensuring rapid and even mixing. The liquid then flows into a deaeration unit. Inside this sealed vessel, the drink is atomized into fine droplets under vacuum. Dissolved oxygen is extracted while carbon dioxide is introduced. This prevents oxidation, preserves flavor integrity, and prepares the drink for carbonation. Carbonation takes place in a pressurized tank known as the carbonator. Here, the chilled beverage is exposed to a steady stream of carbon dioxide gas. The pressure inside is typically maintained at 3 to 4 bar, and the liquid temperature is kept just above 0 degrees Celsius. These conditions maximize CO2 solubility. Porous stones or fine nozzles distribute the gas, ensuring uniform saturation throughout the tank. Agitators gently rotate to avoid stratification while preventing bubble escape. Meanwhile, packaging lines are activated. If plastic bottles are manufactured on site, polyethylene terephthalate preforms are loaded into a rotary feeder. Each preform is gripped and passed through an infrared heating oven, where the plastic softens. Inside a blow mold cavity, the preform is inflated with high pressure air into its final shape. Bottles emerge, fully formed and warm to the touch. Air conveyors guide them toward rinsing. Rinsers invert each bottle and spray sterile water into the interior. The bottles are then dried with air knives and positioned upright for filling. They enter a rotary isobaric filler, where pressure is equalized between the bottle and the drink to preserve carbonation. Each bottle is locked into a filling valve. First, carbon dioxide gas purges the empty space, preventing oxygen contamination. Then the valve opens and the carbonated Fanta flows upward from the base. Foam is avoided through bottom-up filling and controlled turbulence. When the fill line is reached, the valve shuts instantly. Excess gas is vented and the bottle is released onto the next conveyor. Caps arrive from a centrifugal sorting bowl. They are aligned, sanitized, and fed toward the capper, where a torque head presses and twists each one onto the bottleneck. The torque is monitored by a feedback sensor that checks every closure in real time. Any bottle that fails to meet torque specs is diverted automatically from the line. A high-speed inkjet printer then marks each bottle with production codes, timestamps, and batch identification. These markings are inspected by vision systems that confirm legibility and placement. Additional cameras check fill height and cap alignment. Bottles failing any inspection are rejected through pneumatic actuators. Labeling follows. A roll-fed labeler applies either pressure-sensitive or glue-applied labels depending on the format. The label roll unwinds, cuts to length, and wraps each bottle in a single smooth motion. Rollers press out any air bubbles, and sensors verify label position. Adjustments are made automatically based on visual feedback. Labeled bottles are grouped into packs at the bundling station. A servo-controlled collator arranges them into 12s, 6s, or 24s depending on product format. A plastic shrink film wraps around the group, and the pack passes through a heat tunnel. Hot air shrinks the film tightly, locking the bottles into a unified pack. The packs move on to palletizing. A robotic arm with suction cups or mechanical clamps picks up each bundle and stacks it on a pallet in alternating patterns. Slip sheets are added for stability. Once a pallet is full, it's moved into a stretch wrapper. A rotating arm wraps plastic film under tension from the base to the top of the stack. This secures the load for transport. Parallel to the bottle line, aluminum cans are processed on a separate track. Empty cans arrive by depalletizer and enter a rinser. After internal cleaning, they flow into a high-speed rotary filler. Isobaric pressure filling minimizes gas loss. Immediately after filling, the cans pass into a seamer where a metal lid is dropped and double seamed with extreme force and precision, sealing in the carbonation. Cans are coated, checked, and shrink wrapped into trays, then palletized, just like bottles. Every mechanical step is governed by programmable logic controllers. These devices receive data from sensors monitoring flow rates, temperatures, torque values, fill levels, and carbonation pressure. If any parameter drifts beyond tolerance, the system adjusts in real time or stops the line. All systems communicate through a central SCADA interface, which displays status updates, alarm logs, and production metrics. Carbon dioxide is supplied from insulated bulk tanks located outside the plant. The gas enters the process through a vaporizer and filtration unit. Inline pressure regulators and flow restrictors ensure stable CO2 supply at all stages, from de-aeration to final carbonation. Clean-in-place systems activate between production cycles. A series of automated valves switch flow from product to detergent solution. Heated caustic cleans the tanks, pipes, carbonator, and filler valves. A rinse follows, and finally, a sanitizing solution is circulated. No disassembly is required. The process is monitored by conductivity meters and temperature sensors to verify cleaning effectiveness. Each segment of the Fanta production line is built for modularity and speed. Conveyor belts stretch across the plant in smooth arcs, synchronized by servo motors. Air conveyors are used in bottle transport to prevent mechanical contact. Accumulation zones between machines allow buffer space, so the line continues running even if one unit slows down. Production speeds for bottles can exceed 60,000 units per hour. Lines can operate at over 120,000 units per hour. The entire system is balanced to prevent bottlenecks. Fillers, labelers, and palletizers adjust their speed based on feedback from downstream equipment. Fill level is controlled to within 1.5 milliliters. Carbonation is regulated within a tolerance of 0.05 volumes of gas. Cap torque is checked to within 1 Newton meter. These tolerances are enforced by constant feedback and precision sensors. Label alignment is maintained through optical recognition. If the label wanders off-center by more than 2 millimeters, the labeler adjusts roller speed and cutter timing. Bundling film is tension controlled to avoid wrinkles or tears. Shrink tunnels have multi-zone heating, each controlled by thermocouples. Fanta's bright appearance comes from precise color dosing. The colorant solution is metered by mass flow controllers that inject it directly into the syrup blend. Any deviation in hue is detected by an inline spectrophotometer. For different flavors and regions, flavor concentrate tanks are changed out through quick connect valves. Each tank is barcoded, and the system will not run unless the correct flavor for the scheduled run is confirmed. All ingredient additions are logged, time-stamped, and tracked through the control network. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control system. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems, allowing rapid changeovers with high accuracy. filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coding, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision. It all starts with malted barley, the soul of the beer. In a factory setting, the malt arrives by truckloads or freight trains already malted at a dedicated malting facility. Malting is a process in itself. Barley is soaked, allowed to germinate just enough to activate enzymes, and then dried and kilned to stop the growth. This controlled germination unlocks starches and enzymes that will later convert to fermentable sugars. The exact roast of the malt, pale, caramel, a chocolate, black, determines much of the final beer's color and flavor. For large-scale beers, base malts are used, usually lightly kilned, with small amounts of specialty malts blended in. The malt is piped into massive silos at the brewery, where it's stored dry and clean. When brewing begins, the malt is sent through a series of conveyors or airlifts to the mill. Here, roller mills crush the grain, not into flour, but into coarse grist. The idea is to crack the husk while leaving the interior accessible. Too fine, and the mash will become sticky and hard to filter. Too coarse, and sugar extraction drops. The grist is collected and weighed, then transported directly to the mash tun where the real transformation begins. In the mash tun, often a stainless steel vat the size of a swimming pool, the grist is mixed with hot water to form a thick porridge-like slurry. This step, called mashing, activates enzymes like amylase, which convert starches into simple sugars. The temperature is held precisely, usually around 65 and 68 degrees Celsius, depending on the style of beer. Too hot and the enzymes are denatured. Too cold and the starches won't fully convert. The mash is gently stirred using mechanical arms to ensure uniformity. For the next hour or so, the grain slowly transforms into a sweet liquid known as wort. When conversion is complete, the mash is transferred to the lautering vessel, sometimes built into the same tank. Lautering is the process of separating the liquid wort from the spent grain. A false bottom or fine slotted plates allow the liquid to drain through, while the grain bed itself acts as a natural filter. More hot water, known as sparge water, is sprayed over the top to rinse out every last bit of sugar. The collected wort flows to the brew kettle, while the spent grain, now protein-rich but sugar-poor, is conveyed out of the system. Many large breweries donate or sell this grain to farms as cattle feed. Next is the boil. In towering stainless steel kettles, the wort is brought to a rolling boil and held there for 60 to 90 minutes. This step sterilizes the liquid, halts enzymatic activity, and causes unwanted proteins to coagulate and fall out of suspension. It's also when hops are added. Hops are the cone-shaped flowers of the Humulus lupulus plant, prized for their bitterness, flavor, and aromatic oils. In a factory setting, hops usually arrive as compressed pellets for consistency. Early additions bring bitterness. Late additions and whirlpool hops contribute aroma and flavor. Boiling is carefully managed. A powerful steam jacket heats the vessel, while a system of condensers captures volatile compounds and steam vapor to reduce environmental impact. The smell during this stage is unmistakable. Sharp, herbal, sweet, and slightly pungent. It's the moment beer begins to take on its final character. After the boil, the wort must be rapidly cooled. This happens in a plate heat exchanger, where hot wort flows past cold water or glycol in alternating metal plates. Temperatures drop from near boiling to fermentation ready, usually between 10 degrees Celsius and 20 degrees Celsius, in just seconds. In most large breweries, the water used to cool the wort is captured and reused to preheat the next batch, conserving energy. From there, the chilled wort is transferred to fermentation tanks, colossal, conical bottom vessels made of polished stainless steel. Some are the size of small buildings. This is where the magic really happens. Yeast is introduced, either ale yeast or lager yeast. Yeast begins feeding on the sugars in the wort, producing alcohol and CO2 as byproducts. The tanks are fitted with sensors that monitor temperature, pressure, and gravity in real time. If fermentation is too vigorous, pressure is vented. If it's too slow, temperature can be nudged to wake up the yeast. Fermentation can last from a few days for ales to several weeks for lagers. During this time, brewers pull samples to test for alcohol levels, residual sugars, pH, and flavor development. In big factories, this data is fed into digital brewing systems that model yeast health and fermentation curves. If something's off, brewers are alerted immediately. Once fermentation is complete, the beer isn't quite ready. It must be conditioned, held at near freezing temperatures to clarify and stabilize. During this stage, yeast settles out, flavors mellow, and carbonation levels are adjusted. Some factories use centrifuges to speed clarification. Others rely on time and gravity. Filtration may be employed, either with diatomaceous earth, membranes, or cross-flow systems to remove fine particulates and ensure brilliant clarity. For beers that are meant to be bright and shelf-stable, pasteurization may follow, either flash pasteurization or tunnel pasteurization. But not all beer is pasteurized. Many craft-style or draft-only products skip this step to retain delicate aromas. Once the beer is bright, cold, and stable, it's ready for packaging. In large breweries, packaging lines are like choreographed metal highways. Bottling lines can run at 1,200 bottles per minute. Can lines are even faster. Kegs are cleaned, filled, capped, and labeled by machines. Bottles are rinsed, filled under pressure to avoid foaming, sealed with crown caps, and passed through date coders and labelers. Cans are seam locked, rinsed, and pressure checked. Every container is sampled for fill height, oxygen pickup, carbonation, and microbial safety. In some facilities, advanced cameras scan every bottle or can for imperfections in milliseconds. The packaging halls are cold, loud, and almost hypnotic. Conveyor belts twist and curve. Robotic arms stack cases onto pallets. Shrink wrap machines seal entire loads for distribution. Forklifts or automated guided vehicles shuttle product to cold storage, where beer awaits distribution to bars, grocery stores, sports stadiums, and corner shops around the world. But behind the machinery is a deeper layer of quality assurance. Beer is a living product, and even at massive scale, breweries run labs that would rival pharmaceutical facilities. There are microbial labs, sensory panels, gas chromatographs, and mass spectrometers analyzing aroma compounds, esters, sulfur levels, and oxygen ingress. Trained tasters, often called sensory analysts, taste beer daily, blind, and score it against reference samples. A slight change in carbonation or hop aroma is enough to flag a batch for review. And hygiene is non-negotiable. Brewing equipment is cleaned constantly with clean-in-place systems that circulate caustic solutions, acid rinses, and sanitizers through every pipe, pump, tank, and valve. Breweries are designed with sloped floors, airlocks, positive pressure rooms, and filtered ventilation to minimize contamination. Yeast cultures are kept in pure, cryogenically preserved banks, and propagated into sterile fermenters. Even the water is treated, filtered, softened, and dechlorinated to ensure it doesn't introduce off flavors. Despite the scale, there's a strange elegance to the whole system. Every tank, pump, sensor, and pipe is part of a carefully designed loop. From raw grain to finished beer, the factory operates almost like an ecosystem, closed, balanced, and tightly monitored. Nothing is left to chance. Even the CO2 released during fermentation is often captured and reused to carbonate the final product, reducing waste and environmental impact. Bacardi all starts with molasses, a byproduct of sugar refining. Once cane juice has been boiled and crystallized into sugar, what remains is a dark, viscous liquid rich in residual sugars and minerals. Bacardi sources its molasses primarily from the Caribbean and Central America, where sugarcane grows in abundance. Shipments arrive by the ton, offloaded into deep storage tanks that keep the molasses warm and pumpable. Its smell is rich and heavy, deeply sweet, slightly sour, with a roasted, almost smoky undertone. Before fermentation begins, the molasses is diluted with pure water and combined with nutrients to prepare what's known as the fermentation wash. Bacardi uses a proprietary strain of yeast, one that's been carefully preserved and propagated for generations. This yeast is key. It's what gives Bacardi its distinctive profile: clean, light, with subtle fruity esters and very low levels of fusel oils. In a dedicated propagation room, yeast cells are grown in increasingly larger vessels, fed on molasses and oxygen, until they're strong enough to handle full-scale fermentation. The prepared wash, diluted molasses, nutrients, and yeast, is pumped into fermentation tanks, towering steel vessels the size of small silos. Fermentation is fast and efficient, typically 24 to 30 hours. During that time, the yeast devours the sugars, converting them into alcohol and CO2. The temperature is carefully regulated. Too hot, and the yeast dies. Too cold, and it underperforms. Sensors monitor every parameter in real time: sugar levels, temperature, pH, alcohol content. In massive control rooms, technicians watch digital dashboards as each tank ferments with machine-like consistency. The result of this stage is not rum yet. It's a low alcohol liquid called wash or beer, usually around 7 to 10% ABV. It smells nothing like rum. It's sweet, funky, raw. To transform it into the clear, potent spirit known around the world, Bacardi moves to the next phase: distillation. Distillation is where alcohol is concentrated and flavors are defined. Bacardi doesn't rely on pot stills, as many small batch rums do. Instead, it uses continuous column stills, tall, multi-stage distillation towers that can separate alcohol with incredible precision. These columns have trays or packing materials inside that force the vapor and liquid to interact repeatedly, concentrating the alcohol while removing unwanted compounds. The fermented wash is pumped into the column, heated from the bottom, and as it rises, different components evaporate at different heights. Light, clean alcohols rise to the top and are collected. Heavier compounds are left behind and drained off. By adjusting the temperatures and reflux ratios, Bacardi's distillers control the exact cut of alcohol they want to keep. The result is a high-strength spirit, often 85% ABV or higher, that's clear, light, and extremely pure, essential for Bacardi's signature smoothness. But pure alcohol isn't rum yet. The next steps, aging, blending, and finishing, are where the artistry comes in. The raw distillate, also called aguardiente, is diluted down to around 60 to 70% ABV and pumped into oak barrels for aging. Bacardi primarily uses used American white oak barrels, many of which once held bourbon. These barrels are charred on the inside, and over time, they impart color, vanilla notes, spice, and tannins to the rum. In Bacardi's aging warehouses, massive barrel halls with racks stacked to the ceiling. Tens of thousands of casks rest in the tropical heat. The climate speeds the interaction between spirit and wood, making even short aging periods highly effective. Different rums are aged for different durations. Bacardi Superior, the classic white rum, may be aged for as little as 1 year before being filtered. Gold and flavoured varieties rest longer. Premium products like Bacardi 8 or Bacardi Reserva Limitada are aged 8 to 12 years or more. Each barrel breathes. Alcohol evaporates, a phenomenon known as the angel's share, and oxygen seeps in. Over time, harsh edges soften, flavours deepen, and the rum becomes increasingly complex. Once aging is complete, barrels are emptied, and the rum is evaluated. This is where Bacardi's master blenders, trained experts who can detect flavour differences down to the subtlest note, step in. Dozens, sometimes hundreds of barrels are selected and blended together to create a final product with exactly the right profile. Some rums bring fruity notes, others deliver weight or spice, others still provide structure or sweetness. The blender's job is to make the sum better than the parts, and to ensure that every bottle tastes exactly like the last one, year after year. Now comes one of Bacardi's most distinctive processes, charcoal filtration. For Bacardi Superior and other light rums, the blended rum is passed through layers of activated charcoal, often made from coconut husks, to remove colour and certain heavy flavour compounds. This process, inspired by Don Facundo Bacardi himself in the 1860s, strips away rough edges and leaves the rum bright, clean and smooth. Even after aging in oak, the charcoal returns the rum to a near clear appearance while preserving its vanilla and almond undertones. Once filtered, the rum is diluted with ultra-pure demineralized water down to bottling strength, usually 37.5% or 40% ABV, depending on the market. It's then passed through fine mesh filters to remove any remaining particles, chilled to encourage clarity, and tested for stability. Quality checks are constant. ABV, color, turbidity, aroma, flavor, all are measured in both labs and sensory rooms. Finally, the rum is ready to be bottled. Bacardi's bottling lines are massive, high-speed operations, capable of producing tens of thousands of bottles per hour. Empty glass bottles, custom-shaped with embossed bats and logos, are automatically loaded onto conveyors. They're rinsed, filled with rum under pressure, sealed with tamper-proof caps, and labelled with laser precision. Date codes are printed, barcodes are verified. Every bottle passes through inspection tunnels equipped with cameras and sensors to catch defects, underfills, or misplaced labels. From there, bottles are packed into cartons by robotic arms and shrink-wrapped onto pallets. Pallets are barcoded, logged, and stacked in warehouse zones ready for distribution. Bacardi's logistics network spans continents. From a single facility, trucks, ships, and containers move product across the globe. To supermarkets in Spain, beach bars in Brazil, nightclubs in New York, and resorts in Thailand. Behind the scenes, sustainability plays an increasing role. Many of Bacardi's distilleries use renewable energy, recycle processed water, and recover CO2 from fermentation. Spent yeast and distillation byproducts are often converted into animal feed or used in bioenergy systems. Even the barrels, when retired, may be repurposed for furniture, flooring, or smaller barrel aging projects. Waste reduction is not just about economics. It's part of preserving the legacy of the land and the product itself. And yet, for all this technology and scale, Bacardi's rum still carries with it a certain history, a sense of origin. The company was founded in 1862, and though exiled from Cuba in the 1960s, its roots remain in the tropics. The smoothness of Bacardi rum isn't just a technical achievement, it's a philosophy. Every step, from selecting molasses to filtering the final spirit, is guided by an obsession with drinkability. A Bacardi rum should be mixable, approachable, and endlessly clean on the palate. Jack Daniel's begins with a precisely controlled mash bill of 80% corn, 12% malted barley, and 8% rye. The grains arrive in massive quantities by rail and truck and are stored in silos before being milled on-site in Lynchburg, Tennessee. Corn is cracked into coarse grits. Malted barley and rye are milled finer. The grain is moved pneumatically into huge stainless steel cookers where it undergoes a staged cooking process. Corn first, cooked at a high temperature to gelatinize the starches, then rye, then finally malted barley is added as the mash cools to around 65 degrees Celsius. The malt's enzymes convert starches into fermentable sugars. The resulting mash is pumped into one of 64 fermentation vats, open-top tanks made from cypress wood, some more than 80 years old. These vats each hold around 40,000 gallons. Jack Daniel's uses its own proprietary yeast strain, maintained and propagated internally since the early 20th century. Before yeast is pitched, a portion of the previous day's fermented mash is added to the new batch. This sour mash technique helps control the pH and microbial stability of the fermentation environment. Yeast is pitched in liquid form and begins consuming sugars, producing ethanol and CO2. Fermentation lasts 4 to 6 days. The mash foams, bubbles, and gives off heat. During peak fermentation, tanks require constant monitoring for overflow and contamination. Automated sensors track sugar depletion, CO2 output, and temperature curves. Staff monitor the aroma, foam height, and microbial activity daily. When fermentation is complete, the liquid contains roughly 7-9% alcohol by volume. This distiller's beer is pumped into column stills, massive stainless steel and copper columns more than 40 feet tall. Jack Daniel's uses a single-stage continuous distillation process. Beer enters the column at various levels, while steam is injected from below. Alcohol vapor rises, separating from heavier components. The alcohol vapor is routed to a doubler, essentially a pot still operating at atmospheric pressure, where it's condensed, reheated, and distilled again. The resulting clear spirit, often referred to as white dog, emerges at around 140 proof. Before aging, Jack Daniel's performs its most defining step, the Lincoln County process, or charcoal mellowing. This process takes place in vats over 10 feet tall, filled with sugar maple charcoal. The charcoal is made on-site by stacking 2x2-inch thick maple planks into long rows, igniting them with high-proof whiskey and letting them smolder until fully carbonized. Once cooled, the charcoal is ground into chunks and loaded into mellowing vats. The white dog is slowly trickled, drip by drip, through 10 feet of charcoal, taking 4 to 5 days to pass completely through. The charcoal removes fusel oils, aldehydes, and other harsh flavor compounds. The process is gravity-fed and unpressurized, requiring a consistent flow rate to maintain quality. The resulting spirit retains its proof, but emerges smoother and cleaner, with noticeably reduced volatility. Once mellowed, the whiskey is moved into new, charred American white oak barrels, coopered at Jack Daniel's own barrel-making facility. The staves are air-seasoned outdoors for 6 months to 2 years, then assembled, toasted, and flame-charred to a specific level designed to maximize flavor extraction and color development. Each barrel holds about 53 gallons. The inside is blackened from charring, and the wood sugars have caramelized. Barrels are filled at 125 proof and rolled into one of 90-plus barrel houses across the Lynchburg area. These rickhouses vary in size and construction. Some are multi-story wood frame structures, others are steel-clad, but all use passive temperature variation to promote aging. Inside the barrel house, environmental conditions vary dramatically. Upper floors reach 100-degree F+ in summer, encouraging evaporation and faster aging. Lower levels remain cooler and more stable. Jack Daniel's does not rotate barrels between floors, so aging is not uniform. Instead, blending later equalizes the flavor profiles. Barrels are stacked on wooden ricks, often 6 to 7 high. During aging, the whiskey interacts with the wood. Alcohol penetrates the staves, extracting vanillin, lignin-derived compounds, tannins, and hemicellulose breakdown products like caramelized sugars. Oxidation occurs gradually as oxygen seeps through the porous wood. Angel's share evaporation causes the proof to rise over time and concentrates the flavor. Each year, a barrel loses 5% of its volume to evaporation. Maturation time varies by product. Old No. 7 typically ages for 4 to 6 years. Higher end expressions like Single Barrel or Sinatra Select may rest for up to 8 years or more. Throughout aging, barrels are sampled periodically. Staff draw whiskey using a thief and assess it by color, aroma, proof, and mouthfeel. No age statement is printed on standard Jack Daniel's because blending is used to maintain consistency, not target a specific age. When deemed mature, barrels are dumped onto a stainless steel trough, filtered through mesh screens to catch char, and moved to batching tanks. Here, up to 200 barrels are blended into a single batch. Before bottling, the whiskey is chill filtered, cooled to near freezing, and passed through paper or cellulose filters to remove fatty acid esters that can cause clouding in the bottle. For Old No. 7, the spirit is then diluted to 80 proof, using demineralized water drawn from the same cave spring used for mashing. Other products, like bonded or single barrel proof, may be bottled at higher strengths or without filtration, depending on the release. Bottling takes place on high-speed automated lines. Empty bottles are rinsed with pressurized air or filtered water. Filling machines dispense whiskey using gravity-fed nozzles or vacuum-assisted pumps. Bottles are capped with aluminum closures, corks, or synthetic caps depending on the SKU. Labels are applied using roll-fed labelers with electronic eyes that verify positioning. Lot codes and production dates are printed in UV ink or laser etched onto the neck. Every bottle passes under fill level sensors and automated cameras. Defective units are ejected immediately. Bottles are grouped into cases, shrink-wrapped, and palletized by robotic arms. Finished goods are transported to climate-controlled warehouses. Logistics teams track SKU distribution globally. Jack Daniel's is shipped to more than 170 countries. Each batch must meet regional regulatory standards. Export whiskey may require separate bottling or labelling runs to comply with EU, UK, or Asian labelling laws. Quality control labs sample bottles from each run and perform gas chromatography and spectrophotometry to confirm chemical composition. Sensory analysts run blind tastings daily to validate flavor accuracy. Any deviation from the flavor profile, too much wood, too much sweetness, excessive ethanol burn, results in a hold or rework. Spent grain from mashing is pumped to presses, dried, and sold as cattle feed. Wastewater is treated on-site using anaerobic digesters and aerobic ponds before being discharged or reused. Energy recovery systems capture steam from cooking and distillation to heat water for fermentation tanks. Charcoal from the mellowing vats is replaced regularly and either regenerated or disposed of as biomass fuel. Spent barrels are sold to Scotch distilleries, hot sauce producers, and breweries for secondary use. The cooperage also reconditions barrels for use in cask-finished products or special editions. The distillery operates under strict federal and state regulation. Every barrel and bottle is tracked with a unique serial number. Auditors inspect warehouse records, bottling logs, and inventory counts. The distillery maintains TTB-compliant records for every production step, from raw grain receipt to final export certificate. Barcodes and RFID tags on pallets ensure traceability from distillation to retail shelf. Security is tight, bonded warehouses are sealed, and access is controlled. Jack Daniel's uses SAP-based systems for production scheduling, batch tracking, and global inventory management. Brewing, fermentation, and distillation data are logged automatically by PLCs connected to SCADA systems. Operators monitor process parameters in real time on touchscreen interfaces. Alerts are triggered if mash temperature, fermenter pressure, still output, or bottling line speed moves out of range. Scheduled maintenance is performed weekly. Sensors check flow rates, valve positions, CIP cycle effectiveness, and tank volumes continuously. Yeast propagation is handled in a sterile lab with HEPA-filtered air, jacketed tanks, and strict aseptic technique. Each batch of yeast is cryogenically preserved and banked in long-term storage. Lab staff test yeast for viability, contamination, and fermentation performance. Infection events, such as wild yeast or lactic acid bacteria, are rare but can halt production for full CIP sanitization of all affected equipment. Sanitizers include caustic soda, peracetic acid, and steam. Safety inspections and confined space protocols are rigorously enforced, especially around fermentation tanks, high-pressure steam lines, and ethanol vapor zones. Mash cookers and fermentation tanks are cleaned between every batch. Distillation columns are stripped and acid washed quarterly. Mellowing vats are emptied and replenished every few months. Barrels are inspected for leaks before filling. Leakers are flagged and re-co-opted or discarded. Every floor drain, gasket, and pump seal is part of a scheduled inspection checklist. The entire facility is USDA certified for food safety and operates under HACCP protocols. The process begins with water, which forms the base of cherry Coca-Cola. It's not just any water that can be used. It must be highly purified to ensure no off-tastes or impurities interfere with the final product. Upon arrival at the factory, water undergoes a multi-step purification process. First, it is passed through large sand filters to remove visible debris and particulate matter. Next, it moves through activated carbon filters, which strip out chlorine and other organic compounds that could affect the drink's flavor. This step is crucial in ensuring a neutral tasting base. After this, reverse osmosis or microfiltration is employed to remove microscopic contaminants, bacteria, and dissolved minerals. This purified water is continuously tested for pH balance and purity before being approved for use. Now, it's time to introduce the sweeteners, which are responsible for cherry Coca-Cola's characteristic sweetness. The type of sweetener used depends on the region. In North America, high fructose corn syrup is the primary choice due to its affordability and efficient blending properties. In other regions, sucrose from sugarcane or sugar beets is used. HFCS is produced through an enzymatic conversion process that transforms cornstarch into glucose and then into fructose, creating a highly soluble and sweet liquid. The syrup, or sucrose, is delivered in tanker trucks and stored in large stainless steel silos within the factory. Before use, the sweetener is filtered and preheated to ensure it integrates seamlessly with the rest of the ingredients. The next essential ingredient is phosphoric acid, which gives cherry Coca-Cola its slight tang and acts as a preservative. Phosphoric acid is sourced from phosphate rock, which is treated with sulfuric acid to produce a food-grade acid that can be used in soft drinks. This ingredient arrives at the factory in concentrated liquid form and is stored in specialized tanks to prevent contamination. Precision is key when adding phosphoric acid. Even a slight variation in concentration can alter the drink's flavor balance, making it too tart or too flat. Caffeine, another critical component, is added to provide the beverage's stimulating effect. The caffeine used in cherry Coca-Cola is either extracted from coffee beans and tea leaves or synthesized in laboratories to maintain consistency. It arrives in powdered form and must be carefully measured before being dissolved into the syrup mixture. One of the most recognizable aspects of cherry Coca-Cola is its deep brown color, which is achieved using caramel color. Caramel color is made by heating sugar compounds with acids or alkalis, creating a complex mixture of caramelized sugars that provide both color and subtle bitter notes that complement the drink's sweetness. Caramel color must be carefully controlled for shade consistency, ensuring that every batch of cherry Coca-Cola has the same appearance. Now, it's time to add the proprietary natural flavors that define Coca-Cola's unmistakable taste. These flavors, known internally as Merchandise 7X, are a carefully guarded secret, containing a mix of citrus oils, spices, and herbal extracts. The precise blend is known only to a handful of people within the Coca-Cola Company. These concentrated flavoring agents are added in precise amounts, ensuring the signature cola taste remains identical across all global production sites. But what truly differentiates cherry Coca-Cola from its classic counterpart is the cherry flavoring. This is created using natural cherry extracts or synthetic cherry compounds, depending on local regulations and supply chain availability. Natural cherry extracts are obtained through cold pressing ripe cherries to capture their essence, while synthetic cherry flavors replicate the fruity, slightly tart taste using chemical compounds such as benzaldehyde. The cherry flavor must be added in a carefully measured amount to create a perfect balance with the cola notes without overpowering them. Once all the ingredients have been sourced, purified, and prepared, it's time for the next step: creating the concentrated syrup. In a dedicated syrup production area of the factory, large stainless steel mixing tanks equipped with powerful agitators are used to blend the ingredients into a homogeneous mixture. The process starts by heating the purified water slightly to improve ingredient solubility. The sweetener, whether HFCS or sucrose, is then gradually introduced while the mixture is stirred continuously to prevent crystallization. Next, the phosphoric acid is added, providing cherry Coca-Cola with its signature tangy undertone. Because phosphoric acid is highly concentrated, automated dosing systems are used to ensure precise measurement, preventing any deviations in taste. Following this, the caffeine is dissolved in a small amount of warm water before being incorporated into the syrup, ensuring even distribution throughout the mixture. The natural flavors, including the Merchandise 7X blend and cherry flavoring, are then carefully added. These flavor components are typically pre-mixed into an emulsified solution to ensure they disperse evenly throughout the syrup. This step is crucial, as any inconsistencies in flavor distribution can lead to variations in taste between different production batches. Finally, the caramel color is introduced, giving cherry Coca-Cola its signature appearance. Once all the ingredients are combined, the syrup undergoes a multi-stage filtration process to remove any undissolved particles. This is typically done using fine mesh filters or centrifugal separation methods, ensuring that the syrup is smooth and free from any impurities. After filtration, the syrup is transferred to holding tanks, where it is kept under controlled conditions before being sent to the bottling stage. Throughout the syrup production process, quality control plays a vital role. Factory workers take samples from each batch and conduct tests to measure sweetness levels, acidity, and overall flavor consistency. Sensory panels, trained employees who specialize in taste testing, evaluate the syrup to ensure it matches the established cherry Coca-Cola flavor profile. If any discrepancies are detected, adjustments are made before the syrup is approved for bottling. With the syrup now fully prepared, the next step is dilution, carbonation, and bottling. This is where the concentrated syrup is combined with carbonated water and packaged into cans and bottles for distribution worldwide. But before we get to that, the syrup must first be transported to the filling stations in a highly controlled manner. The next phase of production ensures that the correct syrup to water ratio is maintained and that the carbonation process delivers the signature effervescence that makes cherry Coca-Cola such a refreshing drink. Now that the syrup is ready, it's time to move on to the next critical stage: blending the syrup with carbonated water and ensuring that the correct levels of fizziness, taste, and consistency are achieved in every bottle and can. This process is where cherry Coca-Cola transforms from a concentrated mixture into the refreshing, bubbly beverage that millions of consumers enjoy. Now that the concentrated cherry Coca-Cola syrup is fully prepared and stored under controlled conditions, it's time to move on to the next crucial step in the manufacturing process: blending the syrup with carbonated water and ensuring the perfect level of fizziness. This stage is where cherry Coca-Cola takes its final form, transforming from a concentrated mixture into the refreshing, bubbly beverage that millions of people enjoy. The precision involved in this step is critical because even slight inconsistencies in carbonation or syrup dilution can result in an off-tasting product. The process begins with the careful transportation of the concentrated syrup to the filling stations. To prevent contamination and maintain consistency, the syrup is pumped through stainless steel pipes from the storage tanks to a specialized mixing unit known as a proportioner. The proportioner is one of the most vital machines in the entire production line, as it precisely controls the ratio of syrup to water. Cherry Coca-Cola's signature taste depends on the exact balance of ingredients, and any deviation in the syrup to water ratio could result in an overly sweet or weak-tasting beverage. The standard ratio for Coca-Cola products is approximately 1 part syrup to 5 parts carbonated water, but this can vary slightly depending on factors such as temperature and altitude, which can affect carbonation retention. Before the syrup and water are combined, the water must undergo a final round of purification to ensure absolute consistency. Even though the water has already been filtered and purified at the beginning of the process, additional treatment steps are performed just before carbonation. The water is passed through activated carbon filters once more to remove any remaining traces of chlorine or organic matter. Then it is chilled to a precise temperature, usually around 1 to 3 degrees Celsius. Chilling the water at this stage is essential because cold liquid absorbs carbon dioxide more efficiently, which results in finer and longer lasting bubbles in the final product. Now comes the most intricate step: carbonation. The carbonation process is what gives cherry Coca-Cola its signature fizz and enhances the overall drinking experience. Carbon dioxide gas is injected into the chilled water under high pressure using specialized carbonation tanks. These tanks are equipped with fine diffusion plates that allow the gas to dissolve evenly into the liquid, ensuring consistent carbonation levels throughout the entire batch. The CO2 used in this process must be of food-grade quality, free from impurities that could alter the beverage's taste. To maintain the ideal carbonation level, the process is carefully controlled using high-precision sensors that monitor temperature, pressure, and CO2 concentration in real time. Once the water is fully carbonated, it is immediately mixed with the concentrated cherry Coca-Cola syrup inside the proportioner. This must be done swiftly to prevent any loss of carbonation. The high-speed blending process ensures that the syrup and carbonated water mix thoroughly without causing excessive foaming, which could lead to product loss. As soon as the mixture is complete, the freshly carbonated cherry Coca-Cola is sent directly to the filling lines for packaging. However, this must be done under strictly controlled conditions to maintain carbonation and prevent oxidation, which could negatively affect the beverage's taste and shelf life. The next step is the bottling and canning process, where the freshly mixed cherry Coca-Cola is transferred into its final packaging. This stage of production requires highly specialized machinery that can fill thousands of bottles and cans per minute while maintaining product integrity. The bottling and canning lines operate at incredible speeds, and every detail, from the fill level to the sealing process, must be executed with extreme precision. The filling process begins with the preparation of the containers. Whether the product is being packaged in aluminum cans, plastic PET bottles, or glass bottles, each type of packaging undergoes a thorough cleaning and sterilization process before being filled. In the case of aluminum cans, they arrive at the factory in bulk and are depalletized before being sent through an inverted high-pressure air rinsing system that removes any dust or debris. For PET and glass bottles, the process is more intensive. PET bottles are first blown into shape from preforms using heated molds, while glass bottles go through a multi-step washing process that includes detergent cleaning, high-temperature rinsing, and sterilization with ozone-treated water. Once the containers are sanitized and ready for filling, they move along conveyor belts to the high-speed filling machines. These machines operate with incredible efficiency, using precision nozzles to dispense the exact amount of cherry Coca-Cola into each container. One of the biggest challenges in this step is ensuring that carbonation is preserved during filling. To prevent excessive foaming and carbonation loss, the filling machines use counter-pressure technology. This involves pressurizing the container with CO2 before filling it with the beverage, ensuring that the carbonation remains intact and that there is minimal oxygen exposure. As the bottles and cans are filled, they are closely monitored by sensors and automated quality control systems to ensure that the correct fill levels are maintained. Any underfilled or overfilled containers are automatically rejected from the line. The next critical step is sealing, where each container is securely closed to lock in freshness. For aluminum cans, an automated seaming machine places a lid on top of the can and crimps it into place, creating an airtight seal. For plastic bottles, tamper-evident caps are applied using high-speed capping machines, while glass bottles are typically sealed with either twist-off metal caps or traditional crown caps. Immediately after sealing, the filled containers go through a pasteurization or cold sterilization process depending on the packaging type and regional regulations. In some cases, cherry Coca-Cola undergoes flash pasteurization, where the beverage is rapidly heated and cooled to kill any potential microorganisms without altering the taste. However, for many markets, Coca-Cola products are aseptically filled, meaning that the entire bottling process is conducted under sterile conditions, eliminating the need for heat treatment. Once the sealing and sterilization process is complete, the bottles and cans move to the labeling and packaging stage. This is where branding and product information are applied to each container, ensuring that the final product meets regulatory requirements and maintains Coca-Cola's iconic visual identity. Now that the cherry Coca-Cola has been bottled and sealed, the next phase of the manufacturing process focuses on quality control and inspection. Every single can and bottle must meet Coca-Cola's strict global quality standards before it can be shipped to retailers. This process involves multiple layers of testing, from automated inspections on the production line to detailed laboratory analysis conducted by food scientists. Even the smallest deviation in taste, carbonation level, or packaging integrity can result in a batch being rejected, ensuring that only the highest quality product reaches consumers. The first step in quality control takes place immediately after the filling and sealing process. High-speed vision inspection systems are installed along the conveyor belts, using advanced cameras and sensors to examine each bottle and can for defects. These systems check for issues such as underfilled or overfilled containers, misaligned caps, dents in cans, or improperly applied labels. If a container does not meet specifications, it is automatically removed from the line by a rejection mechanism. This automated inspection process allows for the real-time elimination of defective products, preventing inconsistencies from reaching the market. Another crucial quality control measure is the carbonation and pressure test. Since cherry Coca-Cola's signature fizz is one of its defining characteristics, it is essential to ensure that each bottle and can contains the correct amount of dissolved CO2. To verify this, a random selection of containers is taken off the production line and placed into a specialized testing chamber where their internal pressure is measured. If the pressure falls outside the acceptable range, this could indicate improper carbonation levels, a sealing defect, or temperature fluctuations during the filling process. If an issue is detected, adjustments are made to the carbonation equipment to maintain consistency across the batch. Next, samples from each production run are sent to the on-site laboratory for detailed chemical and sensory analysis. Here, trained food scientists perform a variety of tests to confirm that the cherry Coca-Cola meets Coca-Cola's strict formulation guidelines. One of the first tests conducted is the Brix test, which measures the concentration of dissolved sugars in the beverage. Since cherry Coca-Cola has a carefully calibrated sweetness level, any deviation in the Brix measurement could indicate an incorrect syrup-to-water ratio, requiring adjustments in the proportioner. Another key laboratory test is pH analysis. The acidity of cherry Coca-Cola is a crucial component of its taste, and this is largely controlled by the phosphoric acid content. A pH meter is used to measure the beverage's acidity, ensuring that it falls within the required range. Any variation in pH can significantly affect the drink's flavor balance, so this test is performed regularly to maintain consistency. Sensory evaluation is another critical aspect of quality control. A panel of trained taste testers, known as a sensory panel, is responsible for conducting blind taste tests to ensure that each batch of cherry Coca-Cola matches the expected flavor profile. These experts are highly trained to detect even the slightest differences in sweetness, acidity, carbonation, and cherry flavor intensity. They compare samples from the production line with reference samples from previous batches, ensuring that the taste remains uniform across all locations. If any inconsistencies are detected, adjustments are made to the formulation or processing parameters before the product is released for distribution. Packaging integrity is also a major focus of the quality control process. Even if the beverage itself meets all specifications, the packaging must be flawless to ensure product safety and shelf stability. To test this, random samples of filled bottles and cans undergo extreme stress testing. For plastic bottles, drop tests are conducted to simulate potential impacts during transportation. The bottles are dropped from various heights to ensure that they do not crack, leak, or experience cap failure. Cans are subjected to compression tests, where a machine applies controlled pressure to verify their structural integrity. If a can is too weak, it could deform or burst under normal handling conditions. If it is too rigid, it could indicate an issue with the aluminum thickness or the pressurization process. These tests help ensure that every container is durable enough to withstand shipping, storage, and handling by consumers. Another important quality control step is microbiological testing. Although cherry Coca-Cola's high acidity and carbonation naturally inhibit microbial growth, samples are still tested for the presence of bacteria, yeast, or mold. Microbiological testing is performed in a sterile laboratory environment where beverage samples are incubated under controlled conditions to detect any signs of microbial contamination. Even though Coca-Cola products are manufactured in sterile conditions, this extra layer of safety ensures that no contamination occurs at any stage of production. After all of these quality control tests have been completed, the final step before distribution is the batch coding and tracking process. Each bottle and can is printed with a unique production code that contains information about the manufacturing date, production line, and facility location. This allows Coca-Cola to track every product from the factory to store shelves. If an issue is ever discovered in a specific batch, this coding system enables rapid identification and recall of affected products. Once the cherry Coca-Cola has passed all quality control tests, the final phase of production involves packaging and distribution. This step ensures that the product is properly grouped, protected, and efficiently transported from the factory to retailers worldwide. The packaging process is highly automated and designed to handle the massive volume of cherry Coca-Cola produced daily while maintaining efficiency, accuracy, and product integrity. The first step in packaging is grouping the bottles and cans into multi-packs. Depending on the market and retail preferences, cherry Coca-Cola is sold in a variety of formats, including single cans, 6-packs, 12-packs, and larger 24-pack cases. The process begins with an automated system that arranges the bottles or cans into the correct configuration for packaging. High-speed robotic arms carefully align the containers into precise rows, ensuring uniformity before wrapping or boxing. These systems are programmed to adjust the layout based on production requirements, allowing flexibility in the types of multi-packs produced. For aluminum cans, a shrink wrapping system is used to bundle them together into multi-packs. The cans pass through a conveyor where they are tightly wrapped in a thin but durable layer of plastic film. This film is then heated in a specialized tunnel, shrinking it around the cans to create a secure and tamper-proof bundle. This method provides stability during transportation while allowing consumers to easily separate individual cans when needed. In some cases, paperboard carriers are used instead of plastic shrink wrap, particularly in regions where sustainability initiatives encourage the reduction of plastic packaging. These carriers are die-cut to hold the cans securely while allowing easy removal. For plastic bottles, the process differs slightly. Many multi-packs of plastic bottles are held together using plastic rings or shrink-wrapped trays. Larger cases of cherry Coca-Cola bottles are placed into corrugated cardboard boxes for additional protection. The use of recyclable materials is prioritized wherever possible to reduce environmental impact. Coca-Cola has implemented sustainable packaging solutions such as biodegradable plant-based plastics and recyclable wrapping materials to minimize waste. Some factories have also introduced lighter weight PET bottles that require less plastic while maintaining the same durability, further contributing to environmental goals. Once the cherry Coca-Cola bottles and cans are securely packed, they move to the palletization stage. A palletizer is a large automated machine that carefully stacks the packaged products onto wooden or plastic pallets in an optimized arrangement for stability. This process ensures that products do not shift or fall during transport. Each pallet is carefully configured to maximize space while maintaining structural integrity. The palletizer is programmed to create stable layers of product, with each row strategically positioned to distribute weight evenly. After the pallets are loaded, they are wrapped with industrial-strength plastic film to keep them secure. This stretch wrapping process ensures that the products remain stable during transport. In some cases, pallets are reinforced with corner protectors for additional stability, particularly when shipping long distances. Some facilities also use robotic pallet wrappers, which automatically detect the height and dimensions of each pallet to apply the precise amount of stretch film required for stability without excessive material use. Once wrapped, the pallets are labeled with tracking codes and barcodes that contain critical shipment information, including the product type, batch number, expiration date, and destination details. These labels ensure that the inventory can be accurately tracked throughout the supply chain, reducing the risk of misdelivery or loss. The tracking system also allows retailers to quickly verify shipments upon arrival and enables Coca-Cola to monitor stock movement and demand trends. The next step is warehouse storage and inventory management. Once the cherry Coca-Cola pallets are prepared, they are transported via forklifts to massive storage warehouses. These warehouses are temperature controlled to protect the beverage from excessive heat or humidity, which could affect carbonation levels or packaging integrity. Temperature regulation is especially important in regions with extreme climates, as fluctuations in temperature could cause the CO2 in the beverage to expand or contract, potentially leading to leaks or compromised carbonation. Advanced inventory management systems track every pallet, using barcodes and RFID technology to ensure efficient organization and retrieval. These systems automatically log incoming and outgoing shipments, allowing real-time monitoring of stock levels. Warehouses are organized using automated retrieval systems that move pallets using robotic arms and conveyor systems, further increasing efficiency in high-volume distribution centers. Once the products are stored, the logistics and distribution phase ensures that Cherry Coca-Cola reaches retailers and consumers as quickly as possible. The logistics team carefully plans delivery routes based on demand, ensuring that distribution centers and retail locations receive fresh stock on schedule. The distribution model varies depending on the region, with some locations utilizing central distribution hubs that serve multiple retailers, while others ship directly from production facilities to large supermarket chains and wholesalers. Trucks are loaded with pallets of Cherry Coca-Cola according to a strict loading schedule, ensuring that the oldest inventory is shipped first to maintain freshness. The loading process is carefully coordinated to optimize space while keeping products stable during transit. Many of these trucks are refrigerated or climate controlled, particularly in warmer regions, to prevent heat exposure that could compromise product quality. In some cases, insulated truck liners are used instead of full refrigeration, allowing for temperature control without the added energy cost of refrigerated transport.